All right, so get this. Someone wants us to wrap our heads around this whole inflationary universe thing.
Okay.
Specifically, what Alan Guth was proposing back in 1981.
Okay, sounds fun.
Right. He gave us his paper, and whoa, it is dense.
Oh yeah, Guth's paper is a classic, but it's definitely a challenging read.
Definitely. So buckle up, listeners. We're about to dive deep into a universe expanding faster than, well,
Faster than the speed of light, almost.
almost.
Yeah.
And, the listener wants to know how Guth tackled these classic cosmological puzzles, like why is the universe so uniform?
Hmm.
And why is its density so finely tuned?
The big questions.
Huge. Plus, we'll try to touch on implications for things like those magnetic monopoles.
The crowd pleaser.
And of course, no deep dive would be complete without addressing some of the challenges to the theory, right?
Absolutely. Got to look at both sides.
Okay, let's start with the basics. What were the big problems with the standard Big Bang model that Guth was trying to solve with this whole inflation idea?
Okay, well, there were a couple of major head scratchers that really bothered cosmologists. The first is this thing called the horizon problem.
Okay, the horizon problem. Lay it on me.
So picture the universe right after the Big Bang, this tiny, hot, dense soup of particles.
Got it. A cosmic soup.
Right. And the problem is, different parts of this early universe were so far apart that they couldn't have possibly ever interacted with each other.
Like not even a little howdy.
Nope, no way. But somehow they still ended up looking remarkably similar, like eerily similar in temperature and density.
Wait, so parts of the universe that were total strangers somehow ended up with matching outfits?
Exactly, and that's the dilemma. The standard Big Bang model doesn't really explain this uniformity. It's like, finding two identical snowflakes on opposite sides of the planet.
Yeah, that would make you wonder. How could they be so similar without ever bumping into each other?
That's the horizon problem in a nutshell.
Okay, so that's one puzzle piece. What's the other one?
The second one is known as the flatness problem. And this one gets into the whole universe's density thing and its relationship to its shape.
All right, so density and shape. I'm intrigued.
There's a very specific critical density that determines whether the universe will expand forever, collapse back on itself, or kind of hang out in the middle.
Okay, and is our universe at that special density?
Well, observations suggest it's really, really close to this critical density, meaning it's almost perfectly flat.
Flat universe, so what's the problem?
The problem is that, according to Einstein's theory of general relativity, a perfectly flat universe is unbelievably unstable. Like, imagine balancing a pencil perfectly on its tip.
Yeah, good luck with that. One tiny breeze and it's over.
Exactly. So the flatness problem basically asks, why is our universe so incredibly lucky to be so close to this unstable flat state?
Okay, I see. So we've got a universe that's weirdly uniform and precariously balanced on the edge of flatness. And this is where Alan Guth steps in, right, with this inflation thing.
Bingo. Guth basically said, hey, what if in the first, fraction of a second after the Big Bang, the universe went through a crazy period of super fast expansion?
Super fast. Like, how fast are we talking here?
Imagine the space between you and, say, your coffee cup suddenly expanding faster than the speed of light.
Whoa. My coffee would be cold by then.
Yeah, you wouldn't even see it happening. That's the kind of expansion we're talking about. And it all supposedly happened because of something called a false vacuum.
Okay, a false vacuum. Now you're talking my language. Sci-fi stuff. What is that exactly?
It's a pretty cool concept. Imagine a ball resting in a small dip on a hillside.
Seems stable enough?
Right. But even a tiny nudge could send it rolling down at a much lower point. That's kind of what a false vacuum is like. The universe was temporarily trapped in this high-energy state that seems stable, but it's actually just waiting for the right push to drop to a lower, truer energy level.
Okay, so how does this false vacuum cause the universe to go all expansion crazy?
Well, this false vacuum is packed with energy, right? And this energy acts like a supercharged anti-gravity, pushing everything apart at an unbelievable rate.
So basically the universe got blown up like a balloon at warp speed because of this repulsive energy.
Pretty much. And here's the kicker. This crazy, rapid inflation actually solves both the horizon and flatness problems we just talked about.
Wait, really? One idea solves two cosmic mysteries.
It's pretty neat, right?
Tell me how it works.
So remember that snowflake analogy for the horizon problem? Well, think of inflation as like someone shaking the table so hard that all the snowflakes are flung to opposite ends of the room.
Yeah, I'm picturing it.
They're now super far apart, but they still look the same because they were once all clumped together before the shaking started. That's how inflation explains the uniformity we see in the universe today. Everything was once incredibly close together before inflation flung it all apart.
So inflation stretched a small, uniform patch of the universe into the vast, mega universe we see today.
Exactly. Now, for the flatness problem, remember that pencil balancing on its tip. Imagine you could suddenly make the surface it's balancing on like a million times bigger. The pencil might still be a tiny bit off balance, but it would look practically flat.
So inflation smoothed out any initial wrinkles in the universe, pushing it toward flatness.
Exactly, like taking a wrinkled sheet and stretching it taut so it looks smooth.
Pretty clever. But I feel like there was another problem that inflation was supposed to solve, something about magnetic monopolies.
You're right. Inflation also tackles another head-scratcher, the mystery of the missing magnetic monopoles.
Okay, remind me what magnetic monopoles are again.
So basically, they're these hypothetical particles with only a north or south magnetic pole, but not both.
Like a magnet that's cut in half, but only one half exists.
Exactly. And some theories predicted that we should see a lot of them, but we don't. That's where inflation comes in.
Okay, how does inflation explain why we're not swimming in magnetic monopoles?
The extreme expansion during inflation would have basically diluted the concentration of these monopolars, scattering them far and wide, making them incredibly rare and hard to detect.
So inflation spread them out so much that finding one would be like winning the lottery.
Pretty much. Inflation doesn't make them disappear, but it makes them so rare that we might never find one. And that aligns with what we see very few, if any, magnetic monopoles out there.
So inflation solves the horizon problem, the flatness problem, and even explains those missing magnetic monopoles. Sounds like the Swiss Army knife of cosmology.
It does kind of tie things together, doesn't it?
It does, but I have a feeling you can't be all smooth sailing, right? There got to be some catches.
Oh, you're definitely right about that. There are challenges to the theory. And Guth himself pointed out one of the big ones in his paper, a problem with how the universe transitions out of this rapid inflation period.
Ooh, a bumpy landing. This sounds interesting. Tell me more.
Well, it's not as simple as just hitting the brakes on this expansion, you know?
Yeah, that's what I figured. So what happens when you try to slow down this super fast expansion? What's the problem?
The problem is with how this energy from the false vacuum gets released as the universe transitions to a lower energy state. It's like, imagine a pot of water simmering on the stove.
Okay, I'm picturing it.
Eventually it starts to boil and you see all those bubbles, right?
Yeah.
So the transition out of inflation is kind of like that boiling process. But instead of water bubbles, you have these bubbles of a new lower energy phase of the universe forming randomly within the false vacuum.
So the universe is like a pot of boiling cosmic water trying to cool down from all that superheated inflationary stuff.
Exactly. But here's the thing. These bubbles form and collide in a very chaotic, very uneven way. And remember, all that energy from the false vacuum has to go somewhere.
Right, it can't just disappear.
Exactly. It needs to be released to create the particles and all the structures that we see in the universe today. But if this energy release is too messy, well, it could lead to a universe that looks way more lumpy and uneven than what we observe.
So the randomness that kind of helped smooth things out during inflation could backfire when it was time to end the whole thing.
Exactly. That's the challenge. And it's one that physicists have been wrestling with for a long time.
So where does that leave us? Is inflation a bust?
Not at all. Guth's paper was just the starting point. Since then, physicists have been tinkering, coming up with all sorts of tweaks and modifications to the model, trying to address this problem.
So it's like those software updates you get for your phone, always trying to fix bugs and make things run smoother.
That's a great analogy. And speaking of improvements, there's this other interesting aspect of inflation that we haven't touched on yet.
Okay, lay it on me. What have we missed?
Entropy.
Entropy, right. The whole disorder thing.
Yep. So one of the puzzles about the early universe is that it seems to have started in a very low entropy state, meaning it was highly ordered.
So it started organized. Doesn't that kind of break the rules of physics? I thought entropy always increases, like my desk. It only ever gets messier.
You'd think, right. But inflation offers a way out of this. During that period of exponential expansion, the entropy of the universe actually does increase a lot.
Hold on. How is that possible? I thought inflation was all about smoothing things out. That sounds like more order, not less.
It's a bit counterintuitive, but the key is that inflation doesn't just stretch space. It also dilutes the density of any particles or energy that were already there.
So it's like cleaning your room by just adding on more rooms. Same mass, but it's spread out more.
Uh-huh. Yeah, kind of like that. And just like with your room analogy, inflation spreads out the stuff of the early universe, making it less dense, increasing its volume. And this increase in volume leads to a huge increase in the number of possible arrangements of particles, and that's entropy.
So inflation basically cleans up the early universe by spreading things out and increasing entropy.
Exactly. And that actually brings us back to those magnetic monopoles we talked about earlier.
Oh, right. So it solves the monopoles problem, too.
By drastically decreasing the concentration of magnetic monopoles, inflation neatly explains why we don't see them in abundance today.
It's amazing how this one idea inflation can address so many different problems.
It really is. But it's not just about fixing problems with the Big Bang model.
What do you mean?
It also connects to a much bigger picture of physics, specifically grand unified theories.
Oh, right. GUTs.
Oh.
I've heard the name, but I never really understood what they were all about.
Well, they're these theories that try to unify all the fundamental forces of nature into one, elegant framework. And they predict that in the very, very early universe, there were these phase transitions. Kind of like, water changing from ice to liquid to vapor, except we're talking about transitions between different fundamental forces.
Okay, so the early universe was going through some, cosmic makeover.
Exactly. And Guth realized that the energy released during these phase transitions could naturally lead to a period of, you guessed it, exponential expansion, just like what we see in inflation.
So inflation wasn't just some random idea that plopped into Guth's head. It was a natural consequence of these grand unified theories.
You got it. And that's why his paper was so groundbreaking. It wasn't just a patch for the Big Bang model. It was a window into a deeper level of reality, one where all the forces of nature were once unified.
Wow. So we started with these cosmological puzzles, and now we're talking about unifying all the forces of nature.
It's quite a journey. And we've only just begun to explore all the implications of Guth's work.
Some mind-blowing stuff. But didn't you say there was something about those bubbles at the end of inflation that was still a bit of a mystery?
You have a great memory. That's where we'll pick up next time. We'll dive deeper into the challenges and ongoing mysteries of this incredible theory.
All right, so last time, things got a little bubbly.
Yeah, we were picturing the universe basically boiling as it transitioned out of that rapid expansion phase.
Right, and you were saying that the transition might not have been so smooth.
Exactly. The big question that Guth himself was wrestling with was, how do you get this incredible uniformity we see in the early universe if the end of inflation was all chaotic and bubbly?
It's a tough one. It's like saying you can bake a perfectly smooth cake, even if you shake the batter like crazy right before it goes in the oven.
It's a good analogy. So how do you reconcile these two ideas, the smooth universe we see and this messy end to inflation?
Yeah, exactly. Because they seem kind of, incompatible, right?
Right. And physicists have come up with some ideas to try to explain this. One way is to fine-tune the details of the inflationary model itself.
Fine-tuning, huh? What does that even mean in this context?
Well, it's like adjusting the knobs on a really complicated machine. By tweaking things like how fast the false vacuum decays, how the energy is released during the transition, you might be able to create a scenario where those bubbles don't cause too much disruption.
So finding just the right settings so the universe doesn't come out all lumpy.
Pretty much. But fine-tuning isn't the only idea out there. Some physicists have gone a bit more radical, suggesting entirely new mechanisms that might smooth things out, either during or even after inflation.
Okay, now we're talking. Radical ideas.
Yeah.
I like it. What kind of mechanisms?
One idea involves these things called cosmic strings, super dense, one-dimensional defects in space-time. They could have formed during the transition out of inflation, almost like cracks in the fabric of the universe.
Cosmic cracks, wow.
Right.
But aren't cosmic strings supposed to be super energetic, disruptive? How could they help make things smoother?
You're right, they would create some small-scale variations, but their large-scale effects could actually contribute to a more even distribution of matter and energy.
So even though they're creating these cracks, they're also spreading stuff out more evenly.
Yeah, think of it like stirring a thick batter. You might create some little bubbles and swirls, but it helps make sure the batter is mixed evenly. In a similar way, cosmic strings could have smoothed out the universe on a grand scale.
So are there any other smoothing mechanisms people have thought of?
Another one involves something called domain walls, two-dimensional defects in space-time. Imagine, giant invisible walls separating different regions of the universe.
The universe is like a house with lots of rooms separated by invisible walls.
A very big house. And just like walls in a house, these domain walls could influence how things are arranged within the universe. Their interactions might have helped smooth things out during or after inflation.
So many possibilities. And it really makes you realize how much we still don't know about what happened back then.
Absolutely. Inflation is a whole new frontier in cosmology, and we're still figuring it all out. But that's what makes it so exciting. There's so much left to explore.
It's like we've just started to peek behind the curtain of the universe.
Hmm.
And even that little glimpse is mind-blowing.
It really is. Guth's work changed how we think about the early universe, and who knows what other insights we'll uncover about inflation and those very first moments of creation.
Well, this has been quite the journey. I feel like my brain has expanded right along with the universe we've been talking about.
Always a good thing.
Definitely. Big thanks to you for walking us through this. And listeners, we hope you've enjoyed our deep dive into the wild world of the inflationary universe. Until next time, keep looking up, and remember, the universe is full of wonders waiting to be discovered.